Those are the ones we use to radiocarbon date. There are two cores that are really anomalous, these two here. In these cases, we don't find any peat at all, but instead we find these lagoonal deposits, so open water deposits with shell remains that are sitting very nicely, conformably on top of that paleosol. So what these sites indicate is very, very abrupt flooding, basically abrupt drowning and conditions that did not allow any peat to accumulate. And as we will see, that's, the stratigraphy, really key information. This is really the sea level jump that we finally were able to reconstruct. And you can see it's actually very small. It's only on the order of a couple of decimeters. Did a lot of radiocarbon dating. You see a lot of numbers here, but the ones that really matters are the basal peat that is sitting right below this abrupt flooding event, and then the one that appears right above it. And if you look at the ages, you can see that they're almost exactly the same. So, and they're right around 8,200 years old. So this record has really constrained quite nicely the magnitude of the sea level jump associated with that final drainage of Lake Agassiz, and it corresponds in time exactly with the onset of the 8.2 climate event. So these are actually the two samples we're talking about here. And it's important to point out, if you just look at the error bars, you would say like, well, there's nothing special going on here. You can just draw a straight line through this data set. It's really the stratigraphy in between these two data points that kind of gives away that there is something unusual going on. So if we add in this new record and the chronology, it looks like this. And we basically have narrowed things down to, something like 8180 to 8310 years before present. So it seems now that the connection between that Lake Agassiz drainage, sea level rise, abrupt sea level rise, and the climate cooling event is pretty tight. So when we started looking into this problem, our initial assumption was like, well, we just measure the magnitude of sea level rise, and from that we can simply back calculate the freshwater volume that is associated with it. Well, this is where it's beneficial to talk to people like Glenn Milne, who do glacial-isostatic adjustment modeling, so basically look at the response of the crust of the Earth to loading by big ice sheets and how they rebound after you melt away ice and basically load the crust. One of the things that has gained a lot of traction in the last decade or a little bit longer by now is the fact that when you have these large ice masses, they do not only transfer ocean water from the ocean to the continents, but they also change the regional gravitational field in a way, and it's kind of over-exaggerated here. If you imagine a Laurentide ice sheet here, it will pull up the surface of the North Atlantic Ocean towards it. What happens if you abruptly melt a lot of this ice, or even if you do it slowly, it doesn't really matter. You're obviously going to raise sea level on a global scale, but in the near field, near the source of mass loss, you will actually have a net relative sea level fall. It's very counterintuitive, but that's basically what happens. And the implication of that is that if you think about our study area in Louisiana, we are close enough to Lake Agassiz on a global scale that this really matters. To illustrate this a little better, this is a very well-known paper by Jerry Mitrovica that looked at what we call these sea level fingerprints, depending on whether you melt ice in Antarctica or Greenland, or in this case we're talking about mountain glaciers. The sea level fingerprints are going to be very different. So everything indicated here in dark blue will actually be a sea level drop. So if you melt from Antarctica, you have to really move far away to actually get an amount or rate of sea level rise that will exceed the global average. So the bottom line is, if we want to convert our sea level records into meltwater volumes, we have to take this into account. And so that's basically work that was done by a postdoc working with Glenn and Jerry Mitrovica, who looked specifically at Lake Agassiz and its sea level fingerprint. And that actually showed that, as you can see here, anything indicated in blue, if you drain Lake Agassiz abruptly, you will have a sea level fall within this region. And you can see that the Gulf Coast, even here, we're close enough that that signal is probably going to be a lot smaller than the global average. And this actually gave us an opportunity when Mark and I basically started combining our data, and admittedly this is a pathetically small data set, but this is one of the rare situations where you can really test this fingerprint theory, because this event is so abrupt that you can basically neglect everything else that's going on. And what we see here is that these two records, they actually match the theory quite nicely. You know, we have a much smaller amplitude here than we have here. There is actually a new record that will hopefully be published sometime this year from Scotland, and based on what I've seen, it looks like that will be fairly consistent with these other records from the point of view of this fingerprint map. So the implication is that we can actually carry out corrections to obtain these freshwater volumes. There is a number of caveats involved here, and I'm just going to skip over that. They don't really matter too much. If you want to know more, I'm happy to talk about this later. Yeah?
Those maps depend on the volume of water that you're going to release to get the rates that you're getting?
No, it's non-dimensionalized. So it's basically, you know, you can apply it to any volume, and you can say.
But the rates that you're comparing to will change.
Yeah.
Depending on the volume. So how did you fix the volume? Did you use
well,
0.4 and 2 millimeter per year?
Yeah.
Did you use the 0.4 and the 2 meters?
Well, this map is actually not about rates. It's purely about magnitudes.
But you're comparing them to the rates that you saw.
Well, those were magnitudes.
Did you use the magnitudes to assess the volume?
Yeah. Yeah. So basically what we do here is we do the corrections, and you end up with numbers for the Netherlands on the order of 3 meters, and for the Mississippi Delta on the order of 1.5 meters. So there is a difference here. There is actually a reason for it. We believe that this record actually includes 2 phases of Lake Agassiz drainage, and this one only includes 1, namely the very last one. So I think there is a reasonable explanation. The one thing to notice, though, is that if you take that map I showed earlier with that particular volume and convert that to a global average number, it's a lot lower. It's about 0.5 meter. So it's very likely that with that drainage, well, maybe Lake Agassiz was actually bigger than we thought. That could be part of the explanation. But it's likely that there was also a lot of melting ice associated with this drainage, probably a lot of icebergs that allowed us to get at numbers like the ones you see here. So this is basically kind of wrapping up the part of the story around sea level in association with the 8.2 event. What we're doing now is we're trying to push these records further back in time, and I'll kind of make the case why we want to do that with what you see right here. If we think about, for example, the contribution of the Laurentide ice sheet to sea level in the early Holocene, there are very, very different estimates out there in the literature. This is a Dick Peltier's well-known ICE 5G model, which is very widely used, and it assumes that during this 4,000-year interval, the Laurentide ice sheet contributed about 20 meters to global sea level rise. But there are others who assume that the magnitude is much higher, on the order of 30 meters. And this is a really big difference. This is about 1.5 times the Greenland ice sheet. So it's far from trivial. If we go to Antarctica, we basically see similar things. This is actually this is a paper Gene Domack was involved in a few years ago, and if you compare what's suggested here is that during the same time period that Antarctica contributed about 6 meters, but Dick Peltier's model would assume 14 meters. So again, a very, very big difference. The one thing that is kind of ironic is that we often assume that we probably know the least about Antarctica, and that may be true in many ways. I would actually argue that when it comes to this particular problem, the Laurentide ice sheet is in a way even more challenging, because in Antarctica, at least, we still have things like nunataks and trim lines that can tell us something about ice thicknesses. In the case of the Laurentide ice sheet, we really don't have that. So just, even if we know the ice margins very well, we still have to make a reasonable estimate of what the ice thickness was, and that is really, really problematic. And that, that's probably very much a reason why we have these very different estimates out there. So the question is it possible to, get better constraints on the relative contributions from these different ice sheets during the early Holocene with better sea level records? And that kind of brings me to this quote from a review paper on early Holocene sea level that was published a few years ago, and that says, detailed empirically based relative sea level graphs for the full period of the early Holocene sea level rise are disappointingly few. And that is illustrated by some of the relatively few examples that are out there. These are records from all over the world. I'm not going to talk about this in any detail. The point is that they often have very, very large error margins. This is a long record from Tahiti. The scale here is from 0 to 70 meters, so the errors are actually pretty large. And that really prevents us from making a lot of progress on this problem. So if we go here to the Gulf Coast, I want to talk for a little moment about why is it that the early Holocene is so poorly constrained. This is basically a sea level database that was put together by Mark Heima a few years ago. He tried to basically synthesize all Holocene sea level data from the US Gulf Coast, so it probably includes data points from around this region as well. So the one thing we see here is something we see in many, many parts of the world, and that is that for much of the Holocene we have plenty of really nice high-resolution data, and then you get to, say, around 8,000, and then you get this. And obviously this is going to give us a lot less information than this. So the question is, can we improve? And in order to do that, of course, first we have to ask ourselves, why is this in the first place? And there are probably several reasons for this. If we look at these full deglacial records, and it goes all the way back to the Fairbanks record I started off with, these records are generally based on corals. And corals are incredibly valuable to basically reconstruct these, the full sea level rise going back from the last, starting in the last glacial maximum, going forward into the early Holocene. But corals are not very accurate, and the problem is that even the most suitable corals, they have a pretty wide vertical growth range. So the errors are at least 5 meters, and more realistically, probably closer to 10 meters. And that's obviously a problem. So these very high resolution records I showed earlier are often from coastal peats. Not always, there are other sea level indicators that are very good as well, but these are pretty widely available in many parts of the world. But when you go back in time, and we kind of saw that when I showed Frank Lee's work in the early Holocene, these peats get very, very thin and very sketchy. So it becomes harder and harder to find them. So that's why you get this transition into corals, and then suddenly the errors basically start to blowing up tremendously. So the big challenge is, can we do something about this. And the idea that we developed a few years ago with Brad was to start looking at this paleosol that I talked about, because we felt maybe that paleosol is going to stick around longer when we go back in time than those marsh peats. This is another example of what these paleosols look like. Nice, dark gray, organic rich. So basically the idea was to test these paleosols with Brad's ramp pyrolysis carbon dating method. I'm not going to have time to go into any detail on that, but obviously Brad is more than happy to talk to anyone who wants to know more, and I'm sure many of you have heard about this from him. The point here is that if we compare in this particular sample ages derived from this paleosol and compare them to basically stratigraphically equivalent ages from plant macrofossils that are generally provide very consistent results, you can see that they're very similar. They fall nicely on this horizontal line. So that basically means that this is a potentially very useful alternative to using marsh peat. So when we put out our proposal a little bit over a year ago, we tried to make the point, like, we're going to use this to extend our record because we don't really expect to find much in the way of basal peat if we want to go back into the early Holocene with these very rapid rates of sea level rise. So back to this little map. What happened after we submitted a proposal, and this is about almost exactly a year ago, so Spider, who was working on this project at the time, started working in this general area just a little bit outside of New Orleans and made some incredibly exciting discoveries that made me jump in my car and drive out to the field site, and I took the first selfie of my life. So far the first and only. I'm not sure I haven't bought a selfie stick yet, so that's why it's not very well oriented. But the excitement was that she not only found this Pleistocene-Holocene transition at about 25 meters below the surface, which was almost 10 meters deeper than that section around the 8.2 event, but what completely baffled us was that we had peat layers like 20, 30 centimeters. I was stunned. That was basically the last thing I expected. So, and we found it at a number of sites. So that really started changing our thinking about what might be going on. And I'm going to show you now some really preliminary results because we still have a lot of work left to do on this project. But this is basically the part of the record that has been published. So this is basically 8,500 years and younger. And I'm going to add in here the new data that we have so far. And they plot like this. The error bars are still pretty wide. We can certainly improve on this. But the real surprising thing was that if you look carefully, you can see, if anything, the rate of sea level rise in this time interval here is actually slower than it is here. It is certainly not more rapid. So it's basically opposite to what you see on a global scale. And just to illustrate that, I'll show you what is probably our current global standard. This is a very elaborate synthesis of global sea level data, mainly from low latitude regions, by Kurt Lambeck's group. And what it shows is that it shows something quite similar to that Fairbanks curve I showed before. But it clearly shows that when you go back into the early Holocene, that the rate of sea level rise, if anything, it increases. And so it suggests something different than our findings. So if we plot those together, and what I simply did here, I basically looked up data from Kurt Lambeck's record, this global record, and plotted them relative to our data. And you can see a dramatic divergence. Here everything coincides very nicely. And then around this time, our rates are much lower. The globally average rates are much higher. And when you're pushing beyond 10,000 years ago, we're looking at easily 15 meters of vertical separation. So the big question is, what does that mean? And this is basically the hypothesis that we want to test. And in order to test this, we're going to have to rely heavily on our modeler friends, both ice sheet modelers and these glacial isostatic adjustment modelers. But the hypothesis is that the rate of sea level rise on the Gulf Coast may have been much slower than the global average because most of the meltwater came from the Laurentide ice sheet. And that would lead to this gravitational effect that I talked about, that if you primarily melt the Laurentide ice sheet during this time period, then obviously we'll see a major sea level rise on a global scale, but in that region around the source, the rate of rise is going to be much less than the global average. And I'm going to add in some more kind of preliminary observations from other data sources to try to make the case that this may indeed be happening. And so what we're doing here, this is just a very simple table. What we're focusing on here is the time period between roughly 9,000 and 8,000 years ago, where we have data for a few sites around the world. So we have Louisiana. I showed you earlier the data from the Netherlands. And here we have two other sites, one in China and one in Singapore. This is actually the Yangtze Delta. And if we simply look at the rate of relative sea level rise, we do a very simple linear approach, just to get a first order idea, we see that during this time period, which is more or less the same for each of these data sets, that the rate in Louisiana is clearly the lowest. It's a little bit higher in the Netherlands, and it's much higher in Southeast Asia. So all these things together really suggest that there is clearly spatial variability. And probably the simplest way to explain this is to apply this fingerprint theory and say, like, well, it strongly points to the Laurentide ice sheet as being the primary contributor during this time period.
Can you go back to the last one? So that the level, though, is already higher for the Mississippi Delta than the global?
Yeah, so it's basically this slope here we're looking at.
But somehow it got higher earlier,
yeah,
faster.
Yeah, and there are actually reasons for that, which we can talk about later. So basically, so this would be the story, perhaps. And again, it's very preliminary. There are other things that come into play that we can probably resolve by using these models I mentioned. So that's something we plan on doing. But if this story holds up, it will actually potentially also have some implications for meltwater pulse 1A. This is a very, very complicated piece of information. I just put it up here. This is probably the most recent, really high-profile study on